In this lesson, we shall focus on physics, work, energy, and power for grades 11 and 12. We shall look at a series of past exam questions and their applications. Right, and we continue as follows. Right, to start with, we are looking at a rescue helicopter. It's stationary. In other words, it hovers above a soldier. Right. The soldier of mass 80 kilograms is lifted vertically upwards through a height of 20 meters by a cable at a constant speed. Right. Of 4 meters per second. The tension in the cable is 960 newtons. Right. Assume that there is no sideways motion during the lift. Air friction is not to be ignored. Right, so we have exactly this particular question from the first. I have taken this question from you. Okay, now state the work energy theorem in words. Right, we will remember this one and I will just cite it. And we say that the net work, the net work done on an object, right, is equal to the change in kinetic energy, to the change in the kinetic energy of the object, right, of the object, like so. The network done on an object is equal to the change in the kinetic energy of the object. Okay, so this is the work energy theorem stated in words. And move forward. Moving forward, we're going to focus on question 5.2. Draw a labeled free body diagram showing all the forces acting on the soldier while being lifted upwards. Right, so here's the free body diagram. Right, so now you have the force that goes up like this. It is F applied. And then you'd have the force that's going down, which is the weight. And we have friction, because air resistance is not to be, air friction is not to be ignored. And so these are the forces that are involved. Right, so we understand that when this soldier of mass 80 kilograms is lifted vertically upwards through a height of 20 meters by a cable. Right, let me check the message here. Let me check let me check the text from now. Good. Why is there force applied? Okay. Why is there force applied? Okay. Good. Because obviously we understand that there is an applied force. And the applied force is the force of how many newtons? 960 newtons, for example. Right, is an upward force. And it is stated here the tension in the cable is 960 newtons, which is the tension in the cable by which this rescue helicopter is actually in tension and is able to keep this man suspended. And we assume that there is no sideways motion during the lift, so air friction is not to be ignored. Right, but we understand that as this man is being hoisted upwards, but also the soldier of mass 80 kilograms is lifted vertically upwards through a height of 20 meters by cable at a constant speed of 4 meters per second. Yeah, so it's something that you need to take note of. Right, yeah, try to think of this now. But now what is very important is that this is the labeled free body diagram showing all the forces acting on the soldier while being lifted upwards. Right. Yeah. Okay. Right. Isn't it tension? Isn't it tension first? It is tension first. But tension is, it's a force. So in this case, I agree with you. We can call it tension. So we can call it tension, applied force, or if we don't want to call it applied force, you can call it tension. If you don't want to call it applied force, you can call it what? Tension. But either way, it is exactly the tension in the rope or in the cable, right? Because vertically upwards through a height of 20 meters by cable at a constant speed, right? But it's being lifted vertically upwards constantly at 4 meters per second. So take note of that. Okay, so take note of that. Right, any question? Any question? Okay, let me see what they were saying there. Okay. Okay. Yeah, so it is obviously a tension. You can call it an applied force, or you can call it a tension. But obviously it is three cables, so you can call it tension because it is three cables there. So you can call it a tension. Okay, you can call it a tension, or you can call it what you call the applied force. Right, it is obviously the tension in the cable that is the case. So you can call it tension. Right, assume that there is no sideways motion during the lift, so air friction is not to be ignored. So we do not ignore friction. Let's move on to the next question. Let's move on to the next question. Write down the name of a non-contact force. Write down the name of a non-contact force that acts on the soldier during the upward lift. Write down the name of a non-contact force that acts on the soldier during the upward lift. Right, the non-contact force. Okay, let me see where to know is saying there. Well done. That is gravity. Thank you so much, Noah. It is what you call the non-contact force that is being obviously referred to is actually what you call the gravitational force. So you can call it the gravitational force. If you want to call it gravitational force, we call it the weight. We call it the weight of the soldier. We call it the weight of the soldier. So now that is the non-contact force that acts on the soldier during the upward lift. Right, it is actually the name of the contact force that acts on the soldier during the lift. It is a gravitational force If you want to call it a gravitational force, you call it the weight of the soldier. And we move forward. We move forward to the next question. Now the next question is 5.4. Take a look at this one. Use the work energy theorem to calculate the work done on the soldier by friction after moving through a height of 20 meters. Use the work energy theorem to calculate the work done on the soldier by friction after moving through a height of 20 meters. Okay, let us use the work energy theorem. Okay, now obviously a couple of things we need to take into account. It is the fact that we have this one, you can call it the tension, yar. And you have also the weight. And we have a smaller force, which is friction. Now, if this is the case, we need to use the work energy theorem, and work W net is change in kinetic energy, and this is the work energy theorem. So with this mentioned, we note, therefore, that you would have the force applied times change in y cosine theta plus the weight itself, right? So you can call it the weight delta y cosine theta which is change in kinetic energy. What is the applied force? 960 newtons. Okay, it is lifted through 20 meters height. And the angle. Okay, let's take a look at this. Now, when you look at the applied force, the tension is actually an upward force. But the 20 meters through which the soldier is lifted is also a vertical displacement, but an upward displacement. So you're going to have that delta y is also upwards. So the tension and the upward force are parallel to each other, giving us exactly an angle of 0 degrees between the two forces. Okay. Yes, now that is the question. Is the initial kinetic energy 0? Okay, then the final is 4. Okay. Right, is the initial kinetic energy 0? Then the final is 4. Okay, let us take a look at that one. Is the initial kinetic energy 0? Remember that this helicopter is stationary, hovers above a soldier. The soldier of mass 80 kilograms is lifted vertically through a height of 20 meters by a cable at constant speed of actually 4 meters per second. Okay, we shall get to that. Is the initial kinetic energy 0? Is the final one then 4? Okay, is the initial velocity 0? Is the final one 4? Etc. But look, here's the question. The question says, use the work energy theorem to calculate the work done on the soldier by friction after moving through a height of 20 meters. Okay. Okay, we are coming to that now. We're coming to that. So now, what is the weight? The weight is mg. So that you have 80. Okay, so that you have the mass. What is the mass of the soldier? 80 kilograms. So you're going to have exactly 80 kilograms. Right, through that height. So now we have mg, which is 9,8 meters per second. The height is 20 meters. Cosine of what? Okay, now we take the weight. The weight is straight down. And the delta y is upward. Like we said some time back, then the angle between them is 180 degrees plus the work done by friction. The change in the kinetic energy is 0 because we have constant speed. So when the speed is constant and we are saying calculate the work done on the soldier by friction after moving through the height of 20 meters, the speed was constant, and therefore the change in the kinetic energy is going to be 0 because the initial kinetic energy and the final is 0 when the speed is constant. Right, so we're good. Let's continue. Let's continue. Let's continue. Okay. Let's take a look at these. 960 times 20. 19,200. 19,200. Okay, and then now you come to this one. This one is going to be negative. Right, but let us confirm what this one is going to be. Okay, 80 times 9.8 times 20 times cosine 180 degrees, which is minus 15,680. Minus 15,680. Minus 15,680 plus work done by friction equals 0. Now we're going to do the 19,200 minus 15,680. Let us perform the calculation here. 19,200 minus 15,680. That is exactly 3,000. It's exactly 3,520 joules. So it's exactly 3,520 joules plus the work done by friction equals 0. So that the work done by friction is minus 3,520 joules. And this is exactly the work done on the soldier by friction moving through the height of 20 meters. Remember that this friction will essentially be determined when this soldier is in motion through 4 meters per second of speed there. So now you need to think about this and make sure you sort of understand what is happening here. Because in this case, what is then happening is that this soldier is being hoisted, is being lifted up vertically. But you see, during the lifting, a couple of things are taking place, like your friction begins to work effectively as this soldier is being lifted upwards through the air. Right, so we're good. And we try the next question. Try the next one. In the next question, we have a 3-kilogram block. There it is. Slides at a constant velocity of 7 meters per second along a horizontal surface. It then strikes a rough surface. Okay, it's a bit rough here, but it was sliding at a constant velocity of 7 along a horizontal surface. Now, before it then afterwards, it strikes a rough surface, causing it to experience a constant friction force of 30 newtons. The block slides 2 meters under the influence of this friction force before it moves up a frictionless ramp inclined at an angle of 20 degrees to the horizontal, as shown in the diagram below. The block moves a distance d up the ramp before it comes to rest. Show by calculation that the speed of the block at the bottom of the ramp is 3 meters per second. We need to show that the speed at the bottom of the ramp is 3 meters per second. A couple of things that we're going to take into account here. It is most certainly the fact that we can actually be in a position to do these with so much ease, but great simplicity. Right, and we can use the fact that we know W net. W net is change in kinetic energy. W net is change in kinetic energy. So that F delta X cosine theta. Right, the work net, W net, which is the work done, total work done. It's F delta X cosine theta. And then you have 1/2 m v final squared, 1/2 m v initial squared. Now, there are a couple of things that remain very important here. We know that at this point, you would have the mass. Right, and this mass here, and you also have the displacement. So that then in the end, but moreover, what else then do we have here? You understand that the friction force is actually exactly 30 newtons. So that at this point, what you then do is that when these blocks slide like this, they're going to be forces that are involved. Friction is in the opposite. As there is some delta X that is happening in the forward direction over the 2-meter displacement. And therefore, you'd have that 30 newtons of force. And then delta x is 2 meters. Okay, take a look at that. Okay, take a look at that. 30. 2 meters. Okay, the 2 meters is in the forward direction and the friction is in the opposite. And therefore the angle between them is actually 180 degrees. So that's what you're going to put here, 100. Cosine of 180 degrees. Cosine of 180 degrees. So that in the end, we have the following. In the end, you have the following. You have half the mass. The mass is 3 kilograms. So you have 3 kilograms. V final squared minus half the mass of 3 kilograms. The initial velocity has just been 7 meters per second right away. Okay. Now, cosine 180 degrees is actually like -1, and 30 by 2 is a 60. Minus 60. One half 3 VF squared minus the half times 3 times 7 squared, which is 73,5. Like that. Because you note that we have the 7 squared. Just to check everything here. Let us check everything here. Not 0.5. 0.5 times 3 times 49. And this is 73.5. You can see 73.5 joules. Okay. Now you take this one, you move to the other side. And you have 3 times 1/2. Right, so, yeah. You would have the 73.5. Right, the 73,5 minus 60. Half times 3 is a 1,5. VF squared. Okay, yeah. Now we continue. What is 73,5 minus 60? It's 13,5. Which is 1,5 VF squared. So you have this one here. You divide by 1,5. So that in the end, you have VF squared. We have the following. (13.5) divided by 1.5. It's 9. And then you take the square root like that. You apply the square root both sides. And this gives you the final velocity is 3 meters per second. Or we're to show by calculation that the speed of the block at the bottom of the ramp is actually 3 meters per second. And that is what we showed here. That the speed of the block at the bottom of the ramp is 3 meters per second. It's 3 meters per second. That we've shown here. 3 meters per second. We move forward. We move forward. And we used the work energy theorem to do this calculation here. Moving forward. Now draw a free body diagram showing all the forces acting on the block in a direction parallel to the incline, whilst the block is sliding up the ramp. Whilst the block is actually sliding up the ramp, you need to draw a free body diagram to show all the forces acting on the block in a direction parallel to the incline. In a direction parallel to the incline. Let's draw a free body diagram there. Now, what then the free body diagram is going to show in 5.2 is that when this block is then W parallel that. Okay, check that. So it's W parallel. W parallel. W parallel. W parallel. So draw a free body diagram to show all the forces acting on the block in the direction parallel to the incline, whilst the block is sliding up the ramp. So it is exactly W parallel. And this is the free body diagram. Because when it slides up the ramp, you need to take note of the fact that it moves up a frictionless ramp. If this ramp is frictionless, it means that there's no friction, but it is sliding up by dint of its momentum. And so the parallel component of the weight is going to be W parallel there. It's going to be W parallel. It's going to be W parallel. So this is the only force you have. It is the parallel component of the weight. That is what you have. Right, in 5.3, calculate the distance D the block slides up the ramp. Calculate the distance D the block slides up the ramp. We want to find D. We want to find D. We want to find D. Take a listen. So the question is, how do we find the D in this case? How do we calculate the D in this particular question? So we proceed as follows. We're going to use W net. So W net is the change in the kinetic energy. The parallel component of the weight. Delta X cosine theta is W net, is 1/2 the mass, B final squared minus half the mass, B initial squared. What is the parallel component? Parallel component of the weight. We know that the parallel component of the weight is actually mg sine theta. Is mg sine theta times their displacement. It's d cosine of what? Cosine of 180 degrees. Why? Because when this parallel component of the weight is straight down like this, we understand that the displacement is, the D is straight up the incline, so that the angle between these two guys here is 180 degrees, just that way. Okay. Right. Right. Now, the block moves a distance up the ramp before it comes to rest. So finally, it's going to rest. It's going to stop. 0 is the final velocity. The mass is 3. The final velocity, the initial velocity, excuse, at the bottom of the ramp, we read that it was 3 meters per second squared. 3 meters per second squared. Yet finally it stopped, and therefore the final velocity becomes 0, annihilating all these and making all these 0. But the initial velocity itself becomes actually 3 meters per second. What is the mass? The mass is 3 kilograms. The gravitational acceleration is 9,8 times the sine of 20 degrees. What is the D? D remains D. We're looking for it. And we have the cosine of 180 degrees equals here. Equals here. Okay, we just have this here. So we have the 3 squared, and 9 by 3 is 27. If you divide 27 by 2, you get actually negative 13,5. Negative 13,5. Like that. Negative 13,5. Negative 13,5. You have 3 times 9.8 times the sine of 20. 3 times 9,8 times the sine of 20 times cosine 180 which is minus 10.06 D. Minus 10.06 D. Write that one down. Minus 10. Okay, so we do that. Minus 10. Minus 10.06 D, which equals minus 13,5. Minus 13,5. So D is minus 13,5 minus 10,06. $13,5. You divide 13,5 by 10.06. The result is 1.34. 1.34. So that now the D is 1,34 meters. 1,34 meters. 1,34 meters. So now think about this, because we have to calculate the distance D. All right, good. You have to calculate the distance D such that, now the distance D such that the block or that the block slides up the ramp. It slides up a distance of exactly 1 decimal comma 34. 1 decimal comma 34 meters up the ramp. Take a listen and try to digest these. Try to make sure you understand these so that in the end, you really are good and can be in a position to interpret these very, very well. And we move forward. We move forward to the next question. We move forward to the next question. Right, in this next question, we have a block. A 5-kilogram block is released from rest. 5-kilogram block is released from rest from a height of 5 meters and slides down a frictionless incline to point P. Okay, it slides down to point P this way as shown in the diagram below. It then moves along a frictionless horizontal portion PQ and finally moves up a second rough inclined plane. It comes to a stop at point R, which is 3 meters above the horizontal. 3 meters above the horizontal. 3 meters above the horizontal. The friction force, which is a non-conservative force between the surface and the block, is 18 newtons. The friction force, which is a non-conservative force between the surface and the block, is 18 newtons. But your friction force itself is basically a non-conservative force. Use energy principles, or using energy principles only, calculate the speed of the block at point P. Okay, take a listen at that. Take a listen at that. Okay, now try to think of this. Using energy principles only, calculate the speed of the block at point P. Calculate the speed of the block at point P. Right, so there are a couple of things that we need to obviously take into account. It is the fact that this 5-kilogram block is released from rest from a height of 5 meters and slides down a frictionless incline. So this incline here is frictionless. It is frictionless. To point P as shown in the diagram below. So now, because it is frictionless, we need to use energy principle. So work done by non-conservative forces is the change in the potential energy plus the change in the kinetic energy. And this is the formula. Work done by non-conservative forces is the change in potential energy plus the change in kinetic energy. But you note that what we're told here is that it was through this frictionless surface. But also, we need to calculate the speed of the block just using energy principles like this. At the point P, it comes, and now we then, okay, it gets to this point here, then what happens there? Then what happens there? So that now you have the work done by non-conservative forces. Work done by non-conservative forces. As this moves here, you have the change in the potential energy, which is mg h final h initial half the mass v final squared v initial squared, precisely like so. But now we understand that there were no friction forces there. This is frictionless, so that the work done by the non-conservative forces becomes identically zero. The mass of the block is 5 kilograms. 5 kilograms. The G is 9.8 meters per second squared. Right, so we have exactly the following notion. As this block is released from rest, a couple of things remain very, very important. What exactly do we have here? The final height becomes 0. Okay. Okay. Let me check where Neville is saying there. Okay, the answer is 9.90. Well done. That is correct. Thank you so much, Neville. That is correct. Thank you so much. I mean, that you're right. You're right. So I'm going to give you a chance to do some of the questions, and you can always send your answers. You can always tell me what answer you're getting, and then we shall do the corrections together. Okay, that's what I'm going to do now moving forward. I think it's a strategy that's going to work. Okay, right. The final height here is going to be 0. Right. So when the final height is 0, what is the initial height? It is 5 meters. Of the mass is 5 kilograms. What is the final velocity? Right, we understand that it was released from rest. And therefore, the final velocity is not known, but it was released from rest with an initial velocity of 0. 0, initial velocity of 0. So that then in the end, you have the following. Five times 9.8 times 5. That is minus 245. Well, with the negative here. So you can write it as minus 245. So it's going to move to the other side, becoming exactly a 245. And therefore now you have the 5 times 1/2, which is 2.5. VF squared. We continue. And then you have 245, you divide by 2.5, which is VF squared. You find the square root. (2.5). So that we have VF equals . So now you have the following. So we have the square root of 245. Okay, obviously you got that. Right, you got that. All right, we have 245 and it is divided by 245 divided by 2.5. You divide this exactly by 2.5 and it becomes what? It becomes exactly 7 the square root of 2. Right, 7 the square root of 2, you can do that, but now it is 9.89, so it's 9.90. I mean, you said that, so you're right on point there now. Right, hello, my dear. Right, so we found here 7 the square root of 2. Right, we found 7 the square root of 2, which obviously you're able to estimate as 9.90. Yes, my dear, meters per second. Sure. Yes, please, my dear.
So besicela ukuthi usungizele imali sikhona ukuthenga amafishi we-99 nesheya wesinafunya.
All right, my dear.
Ngoba sifuna ukuya esikole manje.
All right, my dear. So which is exactly so yeah, you're getting here. All right, thanks, my dear. And then you get here the 9.90. 9.90. So this one here is 9.90. 9.90 meters per second. 9.90 meters per second. 9.90 meters per second. So now this actually becomes therefore the speed. It becomes therefore the speed that we have, okay? So yeah, you can calculate the speed of the block at point P. It is 9.90. Right, so that is what exactly we have here. So you're think about these and make sure, obviously, I mean, you sent me the answers or through the chat, so I'm sure that obviously you understand that. Explain why the kinetic energy at point P is the same as that at point Q. The kinetic energy here is the same as that one there. Explain why the kinetic energy at point P is the same as that at point Q. Okay, let's check this one. It then moves along a frictionless horizontal section PQ, frictionless. Okay. Okay. There is no non-conservative force, yeah? Yeah, so there is no non-conservative force. Well done, well done, well done, well done. Thank you so much, Newar. I mean, you're right, you're right. So there is no non-conservative force. So that obviously to explain here, well done. So there is no non-conservative force, or similarly, you would then have that at this point, you have no friction. You have no friction. And you have a zero resultant force. You have a zero resultant force. All right. So in other words, there's no friction, or you have a zero resultant force. Right. Or you say that there are no conservative forces present. Right. You can also say no conservative forces present. No conservative forces present. No conservative forces present. No conservative forces present. Or you can say that mechanical energy here in 5.2, you can say that mechanical energy is conserved. Mechanical energy is conserved. Mechanical energy is conserved. Mechanical energy is conserved, right? Okay, let me see where to. Yes, good. Thank you so much, Noah. Thank you so much, Noah. Right, good. And then we move forward to the next question. Right, in moving forward to the next question, we're gonna solve the next problem. We're gonna do the next question, and the next question is as follows. Okay, in 5.3, you need to explain the term non-conservative force. Right, this is what I'm gonna explain, and then you're gonna do the rest calculation yourself. Right, so here, now to explain this one, because they're saying the friction force, which is the non-conservative force between the surface and the block, is 18 newtons. 18 newtons. Explain the term non-conservative force. Right, so a non-conservative. A non-conservative force is a force. It's a force for which is a force for which the work done is path. The work done is path dependent. Right. So in other words, right. So a non-conservative force is a force for which the work done is path dependent. That's what we're saying. Is path dependent. So the work done is path dependent. If ever the work done is path dependent, then we have a non-conservative force. Is path dependent. A non-conservative force is a force for which the work done is path dependent. A non-conservative force is a force for which the work done is path dependent. Right, so yeah, take a look at that one. So the work done is path dependent. So we continue. We continue. So we repeat, a non-conservative force is a force for which the work done is path dependent. That is a non-conservative force. The work done is path dependent. Right, and we continue as follows. We continue as follows. We continue as follows. Calculate the angle theta of the slope QR. 5.4. Calculate the angle theta, this one here. Calculate the angle theta of the slope QR. Yup. Calculate the angle theta of the slope QR. 7 marks. Okay, I'm giving you some good 3 minutes. Some good 3 minutes. You try this one. And then I just need the final answer. Then you're going to send me the final answer on the chat, and then we shall discuss it together. You shall send me the final answer on the chat, and then we shall discuss it together. Right, so please, just try that one. Just try that one. And once you're done, please then let us know. So we continue. Okay, so we continue. All right, so please, when you're done, you send the answer on the charts, and then we'll see what to do. You will see what to do. We will see exactly what to do. Right, when you're done, you'll see exactly what to do. Right, when you're done, we'll see exactly what to do. You'll see exactly what to do. We'll see exactly what to do. Right. You send the answer on the charts, please, when you're done, and then we're going to do it. I'm giving you some good 3 minutes. And then when you're done, we're going to discuss together. When you're done, we're going to discuss together. So do it on the charts. And then when you're done, we're going to discuss together. Right. We're going to discuss together when you're done. We're going to solve it together. But first, I want to see what you're going to do. And then when you're done, and then we shall see what to do together. We're going to see what to do together. So, right, let me see what you got. I'm checking the charts now. Yeah, we don't know the length of QR. Yeah. Yes, we don't know the length of QR. So now the QR is not given, but the marks are 7, you see? I just want to see what you're going to do here with this question. Okay, let me see. Let me check the charts. Please try again. Please try again because we're going to discuss it together. So it's not train smash, but I want to see what you're going to do. We're not in a hurry. We're not running. We are not running. Right, we are not running. We are not running. We are not running. We are not running. We are taking our time here. We are not running. We are not running. We are not running. We are not running. Right. Right. We are not running. Hello? Yes. How are you? Wrong number. Thanks. Goodbye. Right, please let me know when you're done. Let me know when you're done. Right. Let me know when you're done. Right. Okay, let me see. I'm checking the charts, please. Okay, that's fine. Okay, so that is the strategy we're going to use. I'm going to give you some minutes. You try the questions and then you do the corrections together so that you know you can like see how well you can do the question, and then we can proceed from there. Right, so this one is way too easy. We want to find the angle theta, and to find the angle theta, we're going to use SOHCAHTOA. We're going to use SOHCAHTOA. And what is SOHCAHTOA? Right, we're going to use SOHCAHTOA. What is SOHCAHTOA? It is the sine. The sine of theta in this particular triangle here, it's the opposite over the hypotenuse. Right, so you can use that because you already know this one, the opposite. So we just need to find the hypotenuse. And to find the hypotenuse, we proceed as follows. So you can put this one in a small rectangle. So that the work done by the non-conservative forces is the change, yeah? Okay. I'm glad that you're able to realize that. So we just need to find the QR. Once you find QR, then we'll just, substitute it in there. So that in this case, then we use the formula work done by non-conservative forces is actually the change in the kinetic energy and the change in the potential energy. Or similarly, we're going to use here the change in the potential energy together with the change in the kinetic energy. Work done by the non-conservative forces is F delta X cosine theta. Okay, we take this one to be delta X up the incline. And then we have delta X cosine theta. Which is mg. Mg H final minus H initial plus half M V final squared V initial squared. Right. Okay, now we continue and then we are good here. We also okay, we good, we awesome. Okay, we are here. Okay. Okay, yeah, we good. Right. Okay. So yeah, the answer is already like in front of us because we have this now and then everything is obvious, but it's just for a formality, just to do the things that are required. So the force itself is what? It's actually now here it is. The frictional force, which is a non-conservative force between the surface and the block, is 18 newtons. So you have 18 newtons. Delta X. Okay, let me see where now it has here. Okay. Okay, that's the thing. We don't have friction. Right? Remember, yes, there was no friction before. There was no friction here. But as it goes up, QR, then it's actually experiencing. Now, for example, the frictional force, which is a non-conservative force between the surface and the block, is 80 newtons. But now it then moves along a frictionless horizontal portion, PQ. PQ is frictionless, and finally moves up a second rough, a second rough inclined plane. So here, this one is rough. But this one is frictionless. 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 So frictionless. This one is rough. But also we know that it then moves along a horizontal portion, PQ. So PQ is also frictionless. Okay. But now the other one, this one QR is, is not frictionless. It has some degree of friction. Okay. The cosine here. Now, when it moves up the incline like this, there's friction, and friction is straight in the opposite. But the delta x is actually, a displacement upward, so that the actual angle between F and delta x is 180 degrees. The mass is 5 kilograms. The G is 9.8 meters per second squared. Okay, let me see what you're getting. Good. How do you find the friction value? How do you find the friction value? It was given. Here, the friction force, which is a non-conservative force between the surface and the block, this friction force is actually exactly 18 newtons. All right, good. So they've given it to us, 18 newtons. That is exactly the friction force when it goes up the rough surface. We agree that it went through frictionless, then rough with friction. So now we're going to actually realize that the only force that's going to be acting here, or one significant force that's going to be acting here, is going to be friction. And the friction is actually 18 newtons, delta x cosine 180. Right, and simultaneously, you have the mass is 5, 9.8. When it goes up like this, then the final height is 3 meters. The initial height, 0. Okay. Plus, the mass is 5. Okay, it stops at the top, 0. And then initially, it was at the bottom here. And when it reached the bottom, we computed the velocity at the bottom. And we found the speed at point P. Explain why the kinetic energy at point P is the same as that at Q. So the speed at P is the same as the speed at Q. Okay. What is the speed at Q? 9.90. And you square this. And you square that. Right. So now we multiply everything here. So we have cosine 180 degrees. Minus 1 times the 18, which is minus 18 delta x. And then we just do the other things here. We just do the other stuff. 5 by 9.8 times 3 minus. Okay. Good. Let me see what Newar is saying there. Okay, good. Yeah, try it. Yes, try it. Okay, 76.65. You're very close. You're very close. Yeah, it is in that proximity. 76.65. It is in that vicinity. Okay, so let us finish this off. Five times 9.8 times 3. 0.5 times 5 times 9.90. You square it. Yeah, we're getting minus 98.025. Minus 98.025. The other questions that are coming for you, Neo. Minus 98.025. So you get here minus 98.025. Okay, want to get delta x? You can use it, you can do it here. So delta x is minus 98. Okay, let's write clearly. Let's write clearly. So we have minus 98. 0.25 divided by minus 18. And we get the answer. If you then have the 98.025 divided by 18, which is exactly 5.4458 meters. So it is actually exactly 5.4458 meters. That is what we got. And therefore, we know that the sine of theta is 3 divided by the delta x, which is 5.4458. So theta is arc sine of 3 divided by 5.4458. Use the calculator. Thank you so much for trying, Noah. That's what we like. Trying. So now you would have this one. You can take its reciprocal like this. Multiplied by 3. Shift sign. Okay, we're getting 33.43. 33.43 degrees. 33.43 degrees. 33.43 degrees. 33.43 degrees. Now, this is exactly the answer. So you're getting 33.43 degrees. That is the angle here, theta. The angle of theta is actually exactly 33.43 degrees. We got it. We got it. We got the angle. And move on to the next question. Here comes a loaded truck. A loaded truck with a total mass of 5,000 kilograms. There is the truck. Travels up a straight incline at a constant velocity of 15 meters per second. At the top of the incline, the truck is at a height of 55 meters above its starting point. The work done by friction forces is 8,5 times 10 to the 4th power joules. Ignore rotational effects of the wheels of the truck. Define power in words. Okay, this is what I'm going to define for you because I don't want you to write an essay, a long thing. I don't want you to write an essay, a long thing. So we're going to say that the rate at which work is done. The rate at which work is done. Like this. If you don't want to say the rate at which work is done, you say that work done per unit time. Per unit time. If you don't want to say power is the rate at which work is done, you say work done per unit time. If you don't want to say work done per unit time, you say the rate at which energy is transferred. The rate at which energy. The rate at which energy is transferred. The rate at which energy is transferred. The rate at which energy is transferred. The rate at which work is done. Work done per unit time. The rate at which energy is transferred. That is power in words. That is power in words. Power in words. Next question. Next question. In the next question, now we need to draw a labeled free body diagram showing all the forces acting on the track as it moves up the incline. Right, as it moves up the incline, there are a couple of things you need to take into account. It has the weight, which is straight down. There's friction that opposes the motion. The applied force by the engine of the truck to keep the truck going. The normal force, which is the upward force by the surface on the truck. So we can identify a total of 4 forces and hence obviously the marks of 4 as well. 4 forces acting on the truck in the process. 4 forces acting on the truck in the process. In the process. In the process. Okay, move on to the next question. So we have 4 forces. If we need to draw a labeled free body diagram showing all the forces acting on the truck as it moves up, we can see 4 forces. We can identify 4 forces and move on. In 5.3, use the work energy theorem to calculate the work done by the engine of the truck to get to the top of the incline. Yep. Continue. We continue. Okay, please try this one. It's 5 marks. I'm giving you some 3 minutes. And then you'll just send the final answer there. Because you need to calculate the work done. If the work done is 10, just send 10 on the charts by the engine of the truck to get to the top of the incline. If it is 15.5, you just type 15.5 on the charts, and then we're going to see. Okay, you have some good 5 minutes maximum time. 5 minutes maximum time. Try it. I want to see what you're going to do. Because it is a loaded truck with a total mass of 5,000 kilograms, travels up a straight incline at a constant velocity of 15 meters per second. This 15 meters per second is actually the truck's constant velocity. At the top of the incline, the truck is at a height of 55 meters above its starting point. The work done by friction forces is 8,5 times 10 to the 4th power. Ignore the rotational effect of the wheels of the truck. Right. We have 5 minutes. Just left is 4 minutes right now. Just left with some 4 minutes. Right. I said we're not in a hurry. We are not in Harare, Zimbabwe. We're not in Harare, Zimbabwe. We are here. Because now, maybe there's a tendency to think that we're in a hurry. No, we're not. We are not in a hurry. So take your time and let me know when you're done with it. 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 And then when you're done, we shall do it. Let me know when you're done with it. Let me know when you're done with it. Let me know when you're done with it. And then we shall do the corrections. Shall do 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 corrections. We read the question again. A loaded truck with a total mass of 5,000 kilograms travels up a straight incline at a constant velocity of 15 meters per second. At the top of the incline, the truck is at a height of 55 meters above its starting point. The work done by frictional forces is 8.5 times 10 to the fourth power joules. Ignore the effect of the wheels of the truck. Use the work energy theorem to calculate the work done by the engine of the truck to get it to the top of the incline. Okay? We read the question again. We are dealing with a loaded truck with a total mass of 5,000 kilograms. The mass is the total mass of 5,000 kilograms, travels up a straight incline at a constant velocity of 15 meters per second. At the top of the incline, the truck is at a height of 55 meters above its starting point. The work done by frictional forces is 8,5 times 10 to the fourth power. So there's work done by frictional forces, because in other words, there's friction when this truck is going up. But you need to ignore the effects of the rotational effect of the wheels of the truck. But we know very well that the work done by frictional force is 8,5 times 10 to the fourth power joules. Right. Right. Yeah, so please, when you're done, let us know, and then we'll do the corrections. We'll do the corrections. We'll do the corrections. We'll do the corrections. Okay, let me see what Neo has done. Okay, the work done is 213, 2500, 213, 2500. Exactly 213, 2500. Let us check this if it is the correct work done. Let us check if this is the correct work done. 213, 2500. Okay, that's fine. So you're saying the work done is 213, 2500. Right, so we're saying here 213. Right, so we're getting precisely exactly that. Right, so we're getting exactly 213, 2500 joules. Okay. You're suggesting this is the work done. That's okay. We're going to just do corrections and we're going to just compare. Yeah, but you still have something to do. Even if we do this 5.3, then you have the next one. Okay, so this is way too easy. Let's start. It is W net. We need to use the work energy theorem, so we just have to use one formula. W net is the change in kinetic energy. So that work done by friction or work done by the applied force together with work done by friction, but with also work done by the weight. Remember that we have this free body diagram where we have the applied force, we have the friction, we have the normal force, and we have the weight. You have the weight. And therefore, this here is equal to change in kinetic energy. Is equal to the change in kinetic energy. And this change in kinetic energy, we can write it as what? Let's check what Neo is saying there. Okay, let's check what Neo is saying. Right. Okay, that's fine, I understand. So take a look, because we use the same formulas all the time. We use the same formulas all the time. That is the truth. They're not a lot. Okay, because you just look like here. Because here they said you need to use the work energy theorem. You need to use the work energy theorem. So to use the work energy theorem, you will do what? You'll have to look at the fact that there is the change in the kinetic energy. What is it? It is half m v final squared minus v initial squared. Okay. Okay, that's a thing. Okay. Okay, let's say that you're saying, okay, the mechanical energy, when do we use the mechanical energy? When to use that? Okay, that's fine. You can use mechanical energy as well, but it's just that in this question, so yeah, you can use mechanical energy here, but mechanical energy works only if there is no friction. Right, so in the event that there is no friction, then you can use mechanical energy. But if there is friction, yes, you can use mechanical energy. But if there is friction, then then you can't use this one. But if there's no friction, then mechanical energy can be used. But at this point, like, we can't use mechanical energy because it's not conserved. Let me see what Neo is saying there. Okay. Yeah, okay. If there is friction, the mechanical energy, you need to be very careful because it's not the same. You need to include friction. You need to include friction. If you're gonna use mechanical energy, you need to use friction. So now the mechanical energy obviously becomes the best to use when you have no friction. Okay. Work done by the applied force. Okay. The work done by friction forces. Now, the work done by friction is this one. So that now you have work done by friction, which is 8,5 times 10 to the fourth power joules, plus so there is work done by the weight. You can write like this: work done by the weight. And the work done by the weight is exactly what? It is exactly mg, right? Mg delta y cosine theta equals 1/2 Vf squared V initial squared. Okay. Work done by friction is minus 8,5 times 10 to the fourth power. The mass becomes 5,000 of the track. G is 9,8. Delta Y is 55 meters. Delta Y is actually exactly 55 meters. $55 meters. Right, so you continue. Okay, yeah. So the mass is 5,000 kilograms, the G is 9,8, and the delta Y, the height here, is actually exactly 55 meters. Now you have something else. You have something else. So, right. Okay. Continue. Okay, yeah. Let me see what they were saying. Right. So yes, no, that is correct. Applied force is always greater. The applied force always greater. Why? Because it is the winning force because it's able to get the track up the incline. So yeah, it is certainly the greater force here, and it is the greatest force amongst the forces that exist. Okay, so that the mass is 5,000 kilograms, the g is 9.8, the delta y is 55 meters. Cosine, right? So you have cosine. We have cosine. The theta itself is exactly what? Okay, so now if you look at this very carefully, you will see that the angle between the delta y and the weight is straight down, but delta y is a vertical displacement, and therefore the angle between them is actually 180 degrees. And therefore, at this point, we know very well that it travels straight up at a constant velocity, so that now the final velocity and the initial are equal to each other, worked on by the applied force. 8,5 minus 5,000. 9,8. Okay, we're just moving this 8,5 to the right, becomes positive, and then you move the 5,000 to the right, it becomes negative, and then we have the 9,8, 55, the cosine of 180 degrees. Right, so that in the end, we have the following result. Let's use our calculator. Let us use our calculator. Let us use our calculator. Never mind that. So we have our calculator, which is exactly this one here. $8.5 times 10 to the 4th power times 10 to the 4th power. Okay, then you delete. Minus 5,000 times 9.8 times 55 meters times cosine of 180 degrees. Right, so with 80. Then you close, and the answer is this one. We're getting exactly 278 with exactly 2 4 zeros. 278 with 4 zeros joules. So we're getting exactly that one. Okay, we're getting exactly that. So we're getting exactly 278. 278, 1, 2, 3, 4 joules. So we move here 1, 2, 3, 4. Right? We can do 1, 2, 3, 4, 5, 6. 2,78 times 10 to the power 6 joules in scientific notation. 2,78 times 10 to the power 6 joules. Right. Okay, so this becomes the answer. Can see there's a small discrepancy there, but the couple of things you're able to see that we had 3 forces: the applied force, the friction, and the weight there. Yeah. Okay, let's see. Yes, it's okay even when you do not use the scientific notation. You can still leave it like that with the many zeros. You can still leave it that way with the many zeros. Yeah, it's okay. But this one, 10 to the power 6. What is 10 to the power 6? What is 10 to the power 6? 10 to the power 6 is a million. 10 to the power 6 is a million. And a million is the megajoules. So you can say it is 3,78 megajoules. But yeah, no, it's not common in metric that you did use the prefix mega to mean million. And therefore, you might just leave it as 10 to the power 6. But we know that, yeah, it is that. But you can move it 1, 2, 3 places and leave it there. 2780 times 10 to the power 3 joules. 2780 kilojoules. 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 You can still write it like that as well. Okay, let us move on to the next question. The next one is yours now. 5.4. Yes, yeah, the lesson is until 12. The lesson is until 12. Okay, the lesson is until 12. The lesson is until 12. Okay, but we continue. The lesson is until 12. Okay. Okay, we'll move on. Okay, then let's look at 5.4. 5.4 says calculate the average power delivered by the engine of the truck if the truck takes 60 seconds to reach the top of the incline. Calculate the average power delivered by the engine of the truck if the truck takes 60 seconds to reach the top of the incline. Okay. Okay, I never think that it is 4633.33. Okay, let's check. Okay, let's check. So it is 46 to the power. So the power is 46. 33.33. Okay, that is the answer we're getting. I would assume that this is in watts. That is the unit. It can be kilowatts. It can be, you know. So we continue. We continue. We continue. We continue. Let's check. Okay, yeah. Let's see what he's saying there. Okay, that's fine. Okay, that's good. Yeah, I will let you know. I'll let you know. Okay, it is in watts and what sounds. Okay, right. I can see that. Okay, now we're gonna do it together. Let's do it together. Now to calculate, to determine the actual power that we need here, we continue as follows. We continue. Remember, calculate the average power delivered by the engine of the truck. Right, calculate the actual power delivered by the engine of the truck in a situation like this. In a situation like this. Right, so now Okay, gonna do it just now. Gonna do it exactly just now. So now we're gonna discuss it together very carefully. But I want to check if obviously your answer is correct, because that is the answer you have given. So we want to know if your answer is correct or not. We're doing it just now, please. And we're looking at the question 5.4. We're looking at 5.4. Okay, the couple of things you need to do, obviously, to solve this particular problem here, you need to take into account the fact that at this point, we actually are able to determine. We are doing 5.4, 5.4, yeah? Right, so 5.4, then you need to remember that power is work done per unit time. Work done per unit time, so that we actually know very well the work done by the engine to get there. We said it is 2,78 times 10 to the 6th power joules divided by the amount of time, 60 seconds. 60 seconds. So that we have 4,63 times 10 to the 4th power. Right, so, 1, 2, 3. Right, 1, 2, 3. Okay, y'all, check this out. But it's going to be exactly 4.63 times 10 to the 4th power watts. Okay, I can use a calculator, just confirm these things. Just confirm everything here. Can use our calculator. So the calculator would be, for instance, for this track question, to this, you have 2.78 times 10 to the 6th power divided by 60. Which is, now you have 46 with 3 threes. Maybe did you miss a single 3? Maybe did I copy that incorrectly? I need to find out. Okay, yeah, but your answer is correct except the decimal place position. Right, so it's 4.63 times 10 to the 4th power, because you move it 1, 2, 3, 4 places. Right, which is exactly that. Now let us move on. We look at 5.5. It's my hope that I include question 5.5. Yes. The truck now returns down the same incline with a constant velocity of 15. Here's the truck. It looks very, very aggressive. But here's the truck, and it is going straight down. Now it returns down the same incline with a constant velocity of 15 meters per second. How will the work done by the engine of the truck on reaching the bottom of the incline compare to that calculated in question 5.3? Write down greater than, smaller than, or equal to. Right. Okay. We continue. We continue. Yep. Okay, no, it's done. And check. Equal. Equal. Okay, I never think that it's gonna be equal. Okay, let us take a look. Let us pause to reason these together. Is it actually gonna be equal or not? We are looking at the question 5 point exactly that. 5.5. Okay, because how will the truck now returns down the same incline with a constant velocity of 15? It's going down with the same velocity of 15 that it went up with, pretty much. How will the work done by the engine of the truck on reaching the bottom of the incline compare So that calculated in question 5.3. We need the work done. Will it do more work? Will it do less work? Write down greater than and smaller than or equal to. Give a reason for your answer. Okay. So it's going to be smaller than. It's going to be smaller than. It's going to be smaller than. And the reason for this is because we know that weight or gravitational force, weight or what we call gravitational force does positive work on the track. Does positive work on the track. Weight or gravitational force does positive work on the track. And that's the reason, so it's going to be smaller than. Okay, we are concluding at 12. I know it's just a little bit after 12. I know it's just a little bit after 12. I think this is very enough for today. But as your home activity, okay, you don't need to copy this down. You don't need to copy this down. But as your home activity, try this one. Okay, okay, yeah, I wanted to see the previous answer. That's fine. Okay, this is the previous answer. We said that it's going to be smaller than. Why would it be smaller than? So it's going to be smaller than. The reason for that is because the weight of gravitational force does positive work on the track. So that's the reason. Okay, let me see what the charts are saying. Right, let me see what the charts are saying. Let me see what the charts are saying. Right, okay, yeah. All right, good. So it's going to be smaller than. Why is it smaller than when now it's going down than when it's going up? Because the weight of gravitational force does positive work on the track. Right. 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 Okay. Right. Yeah. Okay. Let me see. All right. Good. So now this one is your homework. Okay. This one is your homework. This one is your home activity. It's your home activity. It's your home activity, this one. It's your home activity. It's your home activity. All right, being your home activity, you need to try it. A 12-kilogram block is initially at rest at point A at the bottom of a rough. This is rough. Inclined plane. The block is put up the incline by a constant force F, acting parallel to the incline. The block reaches point B, which is at a vertical height of 4.5 meters above the horizontal with a speed of 2.25 meters per second. See the diagram below. Define the term non-conservative force. Define the term non-conservative force, yeah? Okay, good. Okay, good. All right. And then now you would also, after having defined the term non-conservative force, you will draw a labeled free body diagram for the block when it is put up the inclined plane. Okay, so you have just this little homework to do. And then until next time, it was awesome having a discussion. Take care now and have a good day and goodbye. Goodbye, Newell. Right. All right, good. Thanks, Newell. Goodbye.